Good afternoon. So today we are going to start with a summary of the hydrogen atom. Last week we have derived all the results in the sense that we developed the series expansion, we found the wave function and the energy levels of the hydrogen atom. So I'm not going to do this again, of course. I'm just going to summarize and discuss a little bit what are the physical meaning of this result. And this will be very brief. So just to remind you, we had the charge which was positive. That was the center of the hydrogen atom. It was a point charge. In principle, you could add more than one proton in the center. So hydrogen Z is equal 1. That's the simplest case, but Z equal 2 or Z equal 3 is also possible from the point of view of measurement. And we had here one electron that classically would have gone here around the system like the Earth around the Sun. What we have found that the energy levels of the bound states, so there are bound states and there are continuum states. There are bound states, essentially those states where the electron is not too far from the core of the system. Namely, the wave function essentially decays exponentially in space. While the non-bound states are simply non-bound, which means that they have positive energy, they also have asymptotically a wave-like property very far away. So they are called free. What we are interested in is we are only discussing the bound states, so those states that form the atom. If they are not bound, they are like separate in some sense. So we are discussing only negative energy levels because these are the bound states, and the main result that we got is that these energy levels go like 1 over n squared. So n is the quantum number associated with the energy, and it goes like 1 over n squared. And here you have a scale of energy, because this has to have units of energy. So a natural scale is to define because of the potential energy, it's of the type E squared. This is the charge squared because of the interaction. A0 is some length scale. And okay, we need to calculate things. So here we have also Z squared over 2. And soon we will discuss this Z squared. This 2 is not something that you can guess in advance, but you can understand immediately pretty easily that this has to be the scale. Now, what is this A0? So here energy levels are n equal 1, 2, till infinity, and the sign means that the energy is less than 0, which means that it is a bound state. A0 is the radius of Bohr. This radius is more or less the size of the atom. In particular, in the ground state, you have a typical size here. And on this size, the electron is more or less localized. Of course, the electron is not somewhere in space. It means that on this scale of A0, the wave function in the ground state decays. It can be found also very far away, but that will be with a tiny, tiny probability, which decays exponentially. So the most likely measurements of the position of the particle in the ground state will be on the order of A0. A0 is given by h squared over mu E squared. So this is the radius of Bohr. As you can see from the name, it was found before the use of Schrodinger Equation. This was derived, actually these energy levels were derived by Bohr using the old quantum theory. If you remember, Bohr postulated that angular momentum is quantized. He had a very simple quantum theory before the revolution of Schrodinger. And in that simple theory, he derived these formulas which also corresponded to the experiments. So in this system, in this particular system, if you're just interested in the energy levels, the Schrodinger equation is not giving you actually a new prediction. The Schrodinger equation has to be checked more and more to see if it's better than the old Bohr theory. I guess when this appeared, Bohr said, so what? I can get it by my theory. What is the difference? Of course, when you go to more complicated atoms, then you need the Schrodinger equation, and then you'll see the differences between the old theory, and that's why we forget about the old theory, and this is the theory based on Schrödinger's picture. You see here that the radius, you see the bigger is the charge. Imagine you can change the charge. The radius becomes smaller, which makes sense. If you have more attraction, then the size of this guy will become smaller and smaller. It will shrink. This radius, A0, is roughly 0.53 10 to the minus 10 meters. So it's roughly an angstrom. If I assign z equal 1, this number you should remember, because if someone asks you what is the size, roughly the size of an hydrogen, or roughly the size of any atom, it's on the order of this guy. Of course, bigger atoms are a little bit bigger, but this is the typical size of all atoms, at least those with a few electrons, not the bigger ones. So this one you should remember, and also if z is equal 1, another number that most physicists remember is what is E1. So this is for the hydrogen atom. I put in z equal 1. I have this number. I plug in the charge of the electron. We all know what it is in Coulomb, etc. And then we get, this is minus roughly 13.6 electron volt. And this number is important, and the whole picture that we see here is the following picture. So I can plot the Coulomb potential as a function of R. So this is V of R. It is attractive. It goes down to minus infinity, and here it goes like 1 over R, so it goes to 0 here. This is, by the way, the 0 is just a definition. It's just the definition of the potential at infinity. And that's the meaning of this negative, is just the energy that you need to invest in order to take the system, for example, from the ground state. So this ground state is down here, minus 13.6 electron volt. And this is the ground state of the hydrogen atom. And this just means that if you want to take this atom and put it up here, here we have all the continuum states. Continuum means that the energy levels, here you have discrete energy levels, depending on this value of n equal 1, equal 2. So you have discrete energy levels. Up here, all the energy levels are allowed. That's what I mean by continuum. It's not discrete. So here we have a sea of energy level. This is not so surprising, because we know that the particles which are not bound are like free waves. Free waves, what is the spectrum of a free wave? It's like k squared. It's continuous. It's not discrete. So here we have all of them, but we are interested again only in what's going down here in the bound states. So this means, you know, that the wave function here, roughly speaking, will decay exponentially into this region. So here in this region, the classical particle would oscillate here in this energy and never penetrate, and here it will penetrate a little bit. That is tunneling, but it will decay with the decay rate in space with this typical scale A0. So this is the meaning of this thing. So all these, this energy you can also think about. This is the energy. Let us assume that the atom is in the ground state. That is, if you prepare it in a cold state, it will be in the ground state. This is the amount of energy that you need in order to ionize the atom, to break it. That is, to separate the electron from the charge. You need to pump in this amount of energy. Of course, you need to pump in a little bit more, and then this guy will be free, and you'll pump it up here. And if this is the energy balance left, that will be left for its kinetic energy, so it will separate, and then you can measure what's left. So this means that if you pump in energy less than this number, then, well, all kinds of things can happen, but you will not break this the system. So this 13.6 electron volt is important. And of course, we derived all this, but it's very easy to get A0 by hand-waving arguments, just if you want, if you don't remember. So we can claim that, let us do hand-waving. What is hand-waving? We're going to derive some Hamiltonian as a function of some A, where A is a typical distance of this system. And this is actually not an Hamiltonian, this is a quote-unquote Hamiltonian. This is a physicist's approach. So I need to write the Hamiltonian. I need to write it, of course, there is a kinetic energy, more or less. The kinetic energy, you have to have here 2 mu, but this 2 now is just rubbish, I mean, because this is not exact. I even don't write it in 3 dimensions. It's roughly speaking. So here I need to have, what do I need to have here? The Laplacian. The Laplacian is acting on something. It's acting on the wave function. So when you have something that is changing on a scale of A, then this, we don't know what is A. This guy will give you here A squared, roughly. Again, we don't know what's A. Soon I'll give you an argument what is A. So this is just the kinetic energy of the system, roughly speaking. And in addition, you have, let's say Z equal 1. You have also the potential energy, and I put in R, and then instead of R, let us put A. Now, of course, you say, oh, no, you don't need A. Maybe here there's some constants. Of course, this is, of course, correct. I'm not doing anything exact. I'm just, roughly speaking, this is what is the energy of the system. Now, I want to get the ground state. So how do I get the ground state? I look for the minimum of the energy. Because what is the ground state? The ground state is the state where your energy is the lowest. And that means I have to look for some A where this is a minimum. So the ground state, you get the minimum of HA, which means I need to take the derivative of this thing. And if I do so, let us forget constants. You got H squared mu. Mu is the reduced mass. It's essentially the mass of the charge in the center of the system. Here I have A to the 3. I don't care at all about factors because this is obviously very rough. Here you have a plus because this is a minus. Here I take the derivative. So here I have a minus. Here I have a plus, and here I have E squared over A to the power 2. This has to be equal to 0. And then if I multiply, then I get A. This A is roughly H squared over mu here divided by E squared. The fact that I got here exactly the same is just a coincidence. If you want to multiply this by some C, I have no problem. It's just to show you that you can get the order of magnitude, the exact number, you need a calculation. Now, when you look at this expression, you have here this Z squared. It's a little bit surprising at the beginning, but soon I will explain why this happens. Why is it surprising, or why it happens? First, let us assume it's surprising. I mean, I'm not sure it is, but I mean, what I mean by surprising is in the Hamiltonian we have Z times E squared, right? The Hamiltonian you have Z times E squared. So you might say, okay, the charge is like Z E squared, so why do I have this? Maybe you think like that. Maybe you don't think like that. Let us assume you think it's a legitimate question. So where does this Z squared come from? The idea is the following. So you have V of R, which I said is Z E squared over R. Now, roughly speaking, let us look at the potential, average potential, more or less. That is equal ZE squared over R average. Right? But what is, this is again not rigorous, what is R average? You can guess more or less what is R average. It has to depend on Z itself. So this, you can argue, is A0 over Z. So this is more or less equal minus Z E squared over A0. So the bottom line is very simple. Because the typical distance between the center charge and the electron, the scale of the problem will shrink when Z is increasing. So this becomes smaller. Then you have one Z up here, but this guy, roughly speaking, is also becoming smaller with Z, like A over Z. So this Z will come up here, and then you get Z squared here. That is the hand-waving argument, or that's the physics of this Z squared. So this explains Z squared in this main equation. The size must shrink, the size of the atom must shrink with Z. Stronger attraction, smaller atom. Okay, so we now understand this. This is rather easy. Let us now look at the wave functions a little bit, or the states themselves, because they contain much more information. And when you look at the wave functions, of course, then you see the big difference between Bohr and Schrodinger. Of course, not to mention classical mechanics. So what is the energy diagram level? So here I'm going to plot the energy. This is the zero of energy. So I'm going to plot here. This you can think about the potential. I'm going to plot the energy levels here. And I have first, for example, n equal 1. So the wave functions are defined by 3 quantum numbers. And again, we have the explicit expression for the wave function in space. But essentially we have 3 quantum numbers. One of them is n, which corresponds to the energy we discussed. L is the orbital angular momentum, and m is the azimuthal angular momentum. And the solution is some polynomial which decays exponentially times an exponential decay. A polynomial is very difficult. And here you have also the YLMs, the spherical harmonics. So when I fix n equal 1, that is the lowest level, yeah, because the energy is minus 13.6 over n squared. So this is minus 13.6 electron volt if Z is equal 1. So I have here a state. Now, if n is equal 1, we studied last week, there is condition on L. L cannot get all values. It gets values from L equals 0 till n equal 1. So here I have to plot L equals 0. So this state, this is the ground state, which I can write also as 1, 0, 0. Because if L is equal 0, then M is also 0. To make things a little bit more complicated, this has a name. It's called 1s. 1s means, 1 means that n is equal to 1. So 1s, it's a little bit better than these three. 1 means this is the quantum number n. S means L equals 0. Why do we give this name? It's actually history. It's not so important, but many people will use it in many different contexts, in even theory of condensed matter physics. This 1s symbol is used by physicists, and you'll see more. What is the letter S coming from? It comes from the word sharp. So S is sharp. And the reason, I think, I'm not sure, is that long time ago, in the 19th century, people measured the spectrum of the hydrogen atom in the laboratory, and they had some energy levels which are called S, which were sharply seen. So they could see them very easily in the laboratory, so they called them sharp energy levels. Nothing to do with quantum mechanics. It's a historical name. But this S stuck, and it is there until whenever you want. Now let us go to the next level. That is the first exciting state. So the next energy level, so this distance is 13.6 electron volt. This level is 13.6 over n squared, so over 4. I'm not going to plot it really carefully. Here I have another state which also has L equals 0. So this guy also has L equals 0, but its n is 2. So this is going to be 2, 0, 0. So energy state n equal to L, like this one, is 2. All the states here will have L equal to. M is equal to. This is called 2s. But if I choose n equal 2, I can have another L. And this L, I can plot here. And this will correspond to, again, the same energy level, n equal 2. But now orbital angular momentum 1. And here I have, well, I have 3 choices. +1 and -1. If there is no external perturbation, and from an experimental point of view, these energy levels are degenerate, right? So you cannot distinguish them. We're going to call them 2p. So 2p, the p goes for L equal 1, and this is called principal. Again, actually I don't know why. It's like some jargon. We can look now at the degeneracy of these levels. If we neglect the fact that the electron has also spin, so forget about the spin degeneracy. How many states do we have here? Here we have 1, because L equals 1, we have this one. So here the degeneracy is 1 as a function of n. So this is n equals 1. Here n equal 2, so here we have 4 states. And again, this comes from previous lesson. When n is equal to, the possible values that we found previous lesson were 0, L equals 0, and L equals 1. So that's why I stop here. If n is equal to, I cannot find L equal to. That's what we showed in previous lesson. Now we have here n equals 3. So it's not so surprising. Here I'll have 3s, quantum number 3s, L equals 0. And here I have something that we call 3p. And here I'll have something new, which is d. 3d. So here, this is L equal 1. This is L equal 2. So all these guys have the same thing. This comes from diffusive. It means that the spectral line in the experiment was diffusing and was very difficult to detect it, so they called it diffusive. But again, I think most physicists actually don't know the origin. And then it continues, of course, like this. Then you have here 4s, 4p, 4d. Here you have 4f. So we can calculate easily the degeneracy, of course, here comes from two parts. First of all, you have different, if you have one n, you have different L's, and each L has different M's. So, for example, here I have one state, this is F3, and here I have 5. So this is 9. If I have 1, 4, 9, what's the next one? 16, good. Good guess, but you're right. Because this will be generally because simply because f is 2 and you have 5 more, so 9 plus 5 will be 16, and here you see the general rule, this is 2 squared, Gn is, so we have a degeneracy Gn is sum over 2L plus 1. 2L plus 1 is the number of M states. Right? That's the azimuthal number. And I need to sum over L. And the rule was I sum from L equals 0, like here, L equals 0, till N minus 1. You see here, n equal 2, I finish with L equal 1, so n minus 1. And if you do this calculation, you get what you got there. This thing is a simple exercise, it's n squared. So this guy is this is the limitation on L given the quantum number n. As I mentioned previously, this system is an idealized system. So we have only the interaction of the charge in the center of the system with the electron. We can perturb the system, for example, by a small electric field or a small magnetic field. And this will cause some splitting of these energy levels that you can see. And this is how you can count these numbers. It's not that I tell you, okay, they are degenerate, but you cannot measure them. You can measure them by breaking the symmetry, but very slightly, and causing some split here of these energy levels. And this you will learn more in the next semester with something called perturbation theory. Perturbation because you need only the slightest external field, the small one, compared to the strength of the Coulomb interaction to break the symmetry and to remove this degeneracy, and then you can check this theory. It's not that it's totally hidden from us. If there's no perturbation, it's hidden, we cannot measure. But if it is, if you break the symmetry and they split a little bit, you'll see here, this guy is not exactly one, but they have some splitting. And different perturbations cause different splitting. It's a whole field on its own right. Yes?
It's not like the box that you show us last...
It's similar to the box, yes. The box there, the perturbation was physical, that you change the size of the box a little bit. You cannot change here a box. You need to apply an external field, like an electric field or magnetic field. Yeah, but it's similar to what we talked about. Now, what is the intuition here? Why do you have this structure? So, the structure is kind of intuitive. I mean, after you think about it a little bit. So hopefully you have some space in your textbook, because Okay, so the idea is, let us look at L equals 0 first. If you remember what was in the classroom, previous lesson and the one before, we had an effective potential. The effective potential had two contributions. One of them came from the orbital angular momentum. It was like L plus 1 over 1 over r squared. And the other one came from the physical attraction that came from the Coulomb interaction. The orbital effective interaction was just part of the Laplacian that we wrote in special form. That part of the Laplacian I could write as the operator L squared. That was already two or three lessons ago. So the effective potential for L equals 0, there was no contribution at all from the orbital angular momentum, so it was exactly like the Coulomb potential. So here I'm plotting the Coulomb potential and nothing more. What happened when L equal 1? For L equal 1, the same effective potential, there was this repulsion here and it looked like that. The reason was that close to the origin, this guy went like 1 over r squared. It was positive. And this comes from the orbital angular momentum. And what does it mean? It means that when you increase your orbital angular momentum, here only from L equals 0 to L equal 1, also classically you expect the particle to go further away from the origin. And you see here this effective potential is repelling the particle from the core, saying go away because your angular momentum is higher. So this is very physical picture of the effective potential when L is equal 1. Now, let us just look at these two things. So what will happen here? Let us ask two questions. First of all, you have this system and you have that system. Where do you kind of naively or intuitively, well, you have the answer to find the lowest ground state. So somehow, at least for me, it's very natural to assume that this guy has a lower ground state compared to this guy. This, as usual, my drawings are very bad, but the reason is that you added a positive potential. This potential can go to minus infinity because the Coulomb potential goes to minus infinity. And then it's kind of natural that the ground state here will have a lower level than the ground state here. And indeed, you see here, this is the ground state. The ground state of this guy, of this effective L, is this guy. This is this 13.6 electron volt. And this ground state is what you find here. This is minus 13.6 electron volt over 4, right? Because n is equal to here. So this is higher. And this is because the potential doesn't go down, down, down. You have some positive part of the potential. So it's very natural. And this is why we got this gap here. I mean, if you go up here, you don't have this one. And another thing that is very natural, if you have this potential that goes to minus infinity, you can also ask which potential effectively will have more states. Well, the answer is here. You see this guy, both of them have infinite number of states. Because this n continues to infinity. Up here, all the energy levels are very close to one another. Why are they close to one another up there? Because what happens up here, I'm told, up here they are totally continuum. Because that's the free wave. So what happens is that when they approach this 0, the distance between the energy levels becomes very, very small, like 1 over n squared. So if n is in a very big number, this distance is becoming very small. And you see the start of the continuum already below the continuum, becoming denser and denser. And the second thing is here number of states should be larger. Number of states, bound states, larger. It's only by 1 and they're total infinity, so it's infinity plus 1, but it's okay. Then L equal 1. And of course, when you go up to L equal 2, this potential becomes even stronger and it moves towards here, and then you have less states and higher ground states, so to say. Okay, so all this was very intuitive. Less intuitive is what are the wave functions. The wave functions we have calculated previous lesson. I mean, I gave you the iteration rule with which you can, in principle, calculate the wave functions. You remember this polynomial. We have this iteration rule for the polynomial. And the wave functions, their representation in space, not with the bracket. This is a bracket notation, but you have D and L, 2Z, R, n a0 to power L, L 2L plus 1, n plus L, 2ZR, n a0, e to the minus Z, n, ZR, n a0, y, L, m, theta and phi. So of course you don't need to remember this, and if in fact you don't need to copy this because this is just some long equation taken from a textbook. It doesn't really help you. It contains of a few terms. First of all, this guy is simply normalization according to one book. This guy here, you see here, you remember that we had here this demand that the wave function on the origin will not explode. This u over r, if you remember. This guy is the polynomial that we worked hard to calculate, or not exactly calculate, but we showed what is this iteration rule. This is called the associate Laguerre polynomial. So, you know, it's the same story repeated in some sense. You know, for the harmonic oscillator, you have the Hermite polynomials, and here you have other types of polynomials, which are called associated Laguerre polynomials. You go to Wikipedia, and you can find them. Well, it's not so simple, because actually, not like the Hermite, there are two representations of the Laguerre, and this can cause some confusion. So they're associated and non-associated, and different people use different notations. This can cause a little bit of confusion. This is from a book called Saxon, and then you can go simply to page 108, 802 in Kohen-Tanuji, and you get there all the exact formulation, but it's not so important. It just gives you, if you want them very badly, let's say you are calculating something, then you really need to, then you can find them. This DNL is some generally horrible function, 2Zn A0 3 over 2, which, okay, this makes sense because this is the units of the wave function in 3 dimensions. A0 is units of space, and here you have something nasty like this. No one needs to remember this. This you can put in some equation. It just means that it exists. This is the only thing you need to know. I wouldn't even bother. It means that you need to know it on a note, and then you can use it in principle. And even this is just formal, because what is the Laguerre polynomial? Who knows? So for that reason, let us look at the specific solutions, specific wave functions. And we will look at the lowest level let us look at the lowest level states. I mean, there are so many states, we cannot look at all of them, and we wouldn't like to look at all of them. But let us look for beginning at the ground state. So phi 1, 1, 0. If you look at this is for the hydrogen atom. So, okay, this is 1s. This is the ground state. This is z equal 1. So it's hydrogen. And it is given by this formula, pi over a0 to the power 3, 1. So it's very nice to start with. This just means that the polynomial is essentially a constant. And again, these are the units, and you can check normalization, but remember the normalization is with respect to r squared, d theta, d phi, of course. It's normalization in 3 dimensions, but you know how to do normalization in 3 dimensions, I hope. So this is the wave function. You can ask what is the probability. So one problem with all these wave functions is that they are in 3 dimensions, so it's difficult to plot. So people have thought of different ways to just plot them. Of course, if you go to a computer, they can visualize it better than what I can do. But let us look, what is the probability that the particle is between r and r plus delta r. So in this way I go to one-dimensional representation because I just want to know what is the probability that I found the particle at distant r from the origin. So this is proportional to, there is a small issue here that you need to remember, that you need to take into the consideration the fact that you are in 3 dimensions. So if this is the charge, and then let us look at a distance r, and I look, so this is r, and this is r, and this is delta r. So I care not where it is on this sphere, it's a sphere. I just care in this area, which is also coming out of this, what is the probability of finding the particle? So of course, when r becomes bigger, this area inside here is becoming bigger compared to, let's say, small area around here. And this gives you this factor of r squared, which is in the Jacobian of the normalization. So this is given by r squared times phi 110 squared. I mean, but of course, this is minor. You could just plot this guy or whatever you want to plot. So if you choose to plot this guy, so if I plot this guy, phi 100 squared, well, how does it look? Because of this r squared, it's 0 at r, and this is just because the sphere around the origin is very small. So there's a very small probability, and then it goes up. And then it decays, essentially, well, you see here, r squared e to the minus r over 2a0. This is because of the squared. So, but if I looked at a small box, the highest probability would be, of course, to find the particle close to the origin. So this is just a small minor statistical effect that comes from this Jacobian. There are many ways to plot this wave function. So, okay, what is this guy? This is just decaying exponentially. So the easiest way to do is, let's say this is the charge, and then I can plot here something like this. If I was being a good plotter, and this scale is roughly a0, and then, you know, I have the color is fading down with this. So, okay, out here the color is already white, so you don't see it. So this is one way to present this wave function, and the important thing is you have here you have a spherical symmetry. Namely, this wave function doesn't depend not on theta and not on phi, and that's why it's super easy to plot it and present it. So, if I go now, let's say, again, I like L equals 0, M equals 0. These are easier because I have no cosines and no, even phi's are even worse because you need to plot it in a complex plane in principle. So let's say phi 2, 0, 0. So this is the wave function when n is equal to L0, M0. So this is the first excited state, but the orbital angular momentum is simply 0. This is given by 8 pi a squared to the power 3 square root 1 minus r to a0 exponential, again this exponential decay, minus r over 2a0. So you see this n now is 2, so here I have this 2, while here I had a 1. So here you see that the wave function, when r is equal to a, is 0, right? There is a special point when r is equal to 0, it's 2 point, and then if I want to plot this, phi 2, 0, 0, let's say I plot it the same way I did before, times r squared, I will get something like this. This is the 2s state. So why, I mean, essentially this is expected. What is happening here? First of all, again, this is spherical symmetry. There is no angles here. But I get these zeros, but these zeros are not new for you. It's simply because of two things that you know, and one of them is that this wave function has to be orthogonal to this wave function. So if I multiply both of them and integrate, I must, if this guy is always positive, you see here, I took a phase, so this is positive. So here there exists some r which becomes negative in such a way that if you multiply both of them and integrate over all space, that will give you 0. They have to be orthogonal. So it's obvious that this has to have these zeros. And if this is this 0 that you get here at 2a, 0. So that's one reason, just from the fact that they have to be orthogonal. And the second reason is also obvious, that this wave function is like a ground state. So if I have the r squared, then it would be very smooth function, which means that the momentum is low. The kinetic energy is low, so to say, because remember, the kinetic energy is simply the derivative of this wave function. So we had it also for the harmonic oscillator. The ground state was pretty smooth, and as we went up for the harmonic oscillator, the wave functions were wiggling, because then they gained more and more kinetic energy. And here, in addition, something else happens. They move a little bit further away from the origin. Why do they move a little bit to the right? It's also obvious, because this guy has the lower energy. So lower energy, the wave function is closer to where the potential goes to minus infinity, closer to the origin. And now here, this guy has higher energy compared to this one. So this wave function has shifted a bit. It still has something here, but it's less. So if I would plot the first state, it would be something like that. This is 1s. So less, you see with your eyes, or you should be able to see with your eyes, that these wave functions have more kinetic energy, and the potential energy, which is negative, here you go closer to the 0. So you get away from this problem of this minus infinity in the Coulomb potential. Okay. This is all simple, but how will we plot, for example, the 2p level? the 2p level so remember the 2 means that n is equal to, p means l equal 1, and I don't want to plot, you know, in a complex plane, so I'll just take m equals 0. This is what I mean. This is okay here because here I'm considering an ideal hydrogen atom. There's no splitting on the energy level, so these are totally degenerate. And when I plot the square, you remember what is the contribution from, let's say, m equal 1. It's simply I1 times phi or I minus 1 times phi. In the YLMs, when I take the square modulus of it, it will be the same thing. So we totally neglect here this m because it's not important for our discussion. Now this wave function, this we can write it in different ways. For example, 2, 1, 0 in the coordinate representation. This is given by 1 over 4 pi a0 to the power 3 r over a0 e to the minus r over 2a0. That's the 2 is because of this 2 cosine theta. So now we need to plot this guy, but now this guy also depends not only on r, it depends also on theta. So how do you plot this? I mean, okay, it's a 2D plot, but we want to gain some insight. So people use all kinds of representations, and one way to present the cosine is with polar coordinate system. So in the polar coordinate system, this is theta equals 0. This is theta equal 90 degrees. This is theta equal 100 degrees, pi, etc. And of course you have all the other angles here. So you simply take this system and along the direction of your angle, let's say theta is equal 0, what is cosine? Well, it's 1. So you're going to just plot a 1. And then if theta is equal 90, so is this along this direction, well, cosine 90 is simply, or pi over 2 is simply 0. So it looks something like this. Like an 8. One second. So people plot in textbooks all kinds of ways this wave function to gain some insight. So for example here I'll give you this insight. So some people, because this is degenerate, because of the azimuthal number. So the first plots are upstairs here. You see different. Some people like to plot it like this. That is, you have 3 states, right? M equal 1, 0, and minus 1. So symbolically, we can plot this more or less 8 figure, with these 3 representations, but I find this a little bit too much because it's already 3 plots. That is, let us look now, instead of the top figures, let us look on the bottom figures. So you see 1s. Again, 1s was this simple state here. So you have this decay of the wave function, which is exponential, and you see at the center of this 1s, you have a small sphere, and then the dots are a little bit more dense at the end, at the center, because there the wave function is at maximum, and then the density of the dots, goes down exponentially, and then this is the 1s. This is, if you want a picture of the density of the electron in the ground state, this is what it is. Then you go to 2s. So you see here, you have these bang, bang, these type of zeros. So you see the 2s. If you have a good view, namely, you take this picture, you have to also be in your mind be able to rotate it out of the plane of the figure, because it's in 3 dimensions actually. But what you see here is you see these zeros. This zero is between the center line and there are 2 main lines, because you have here, you see, they don't have this R squared, so they have 1 peak, then 0, then 1 peak. The 0 is roughly at 2a 0. I hope all of you can see. You see the zeros in the middle. That is just a spherically symmetric case. But then when you plot this 2p, 2p again is L equal 1 and angular momentum n equals 0, then you need to plot, essentially you see this 8 figure because of the cosine. You see this 8. But it is more complicated because you have also R dependence. And then if you continue, for example, the 3s is kind of obvious, because if you understand the 2s, okay, it had some zeros between these, some peaks where it was centered, then nothing, then peak, then nothing. So when you go from 2s to 3s, you add 1 more peak, because you can imagine that you will get a more complicated polynomial, and then you'll get 1 more peak. And then you see here 3p. So again, you can see with your eye more or less the shape 8, but it is cut off somehow. Why is it cut off? Because this is 3, n equals 3, so you have regions where the wave function is 0. So people would like to plot it like that. And okay, the D case, wow, the D case. The D case looks, it's not like an 8 anymore, because the D case, SPD, D is L equal 2 already. So the D case, you have, what is the D case? The wave function. So for D, D is L equal 2, n equals 3. You can take m equals 0, doesn't matter. So this is this figure here that has a very strange shape. The angular part of the wave function, so phi, is proportional to this cosine to the power 3 minus 1. This comes from the YLMs. So essentially what you see with your eye, these YLMs. And then, let's say, on the diagonal, because this guy can become 0 when theta is on the diagonal. So you see, on the diagonals, you get 0. On the other hand, when theta is equal 90 or 0, which is upstairs and downstairs, and it's not 0, right? It's the peak. So you can see more or less with your eye this structure of this function, or you can believe it. And of course, you also need to understand that there's also spatial modulation. So of course, the further away you go, somehow the density reduces, which is also obvious. So these shapes are non-intuitive, or need some time to get to think about them if you want to. But we will stay with this. Now, all these states that you have now in your hand on this piece of paper, they are very much not in any way similar to Bohr's state, because Bohr's state, you said, what did Bohr say? He said, you have some some orbit that you are rotating around the atom. So the classical case. So what is the difference within the classical case? So what does the classical mechanics say? The classical mechanics says, where is the electron? It's just rotating in a plane. So it's in a plane. All these figures are not plane. Because of course it cannot be in a plane, because then you have uncertainty in the position in one direction, and that would be very bad. So it has to be spread out. That's obvious. We got it in quantum mechanics. But the whole picture of motion in a plane, some plane, is totally gone in these low energy levels. If you want to find the classical behavior, what do you need to go do? You need to go to high energy levels, and this we'll soon do. And we want also to see what is this radius of Bohr that he had this particular motion. So I will not go into the details too much, but essentially this can be done hand-wavingly. So where are Bohr states classical behavior? So this means motion in a plane. Kind of one, of course, in reality, this can never happen. I mean, of course, there has to be some width here, a little bit of width. But if this width is small, then somehow we can neglect it. So this is found for large n. So we want to leave the Schrodinger picture. This is found for large n. But not only for large n. For a particular choice. So if I take n large, but I take L equals 0, what is the shape of the wave function? It's going to be symmetric. It's not going to be, it's going to be like a complicated sphere like I showed you here. Here is in a plane, but it's spheres. One sphere, another sphere, another sphere. Because the wave function will not depend on theta and phi, and that means that you have spherical symmetry. So L equals 0 is not at all a classical state, but this is kind of obvious from classical mechanics, because if you have the sun here and the earth rotating, no one is talking about a state where the angular momentum is 0, right? So L is equals 0 is very quantum, is very non-classical, and you have the spherical symmetry. It's not a motion in a plane. So we want to go to the opposite limit of this L equals 0 to find the classical behavior, and that will be found. What is the opposite of small n? Well, if you have the wave function n, so okay, this has to be n minus 1. So this is my L. It's a very high L, the highest possible. And I'll also choose my m to be at maximum. And this also corresponds to a classical state where you have a motion in a plane, then the total orbital angular momentum is the same as the projection on the z direction, because you always, this is so obvious in quantum, in classical mechanics, you know, you have some angular momentum, you just refer to the direction as z, and that's the total angular momentum is equal to the projection. That's it. So these are what you expect to be quantum states. So if I look at this without this symbol is not alpha, this is proportional to, where I neglect all kinds of numbers. I just want to write down what is the emphasis. Even I neglect units, like A0, blah, blah, all these things. So this guy will be Rn minus 1. One can show this by inspecting the associated polynomials. Here you will have E minus R n A0. This was always in the exponential. And then you have sine to the power n minus 1 theta. And here you have e to the minus I n minus 1 phi. Minus or plus. Plus, I think. Doesn't matter though. This comes from the YLMs. This is I choose L equal n minus 1 and n is big, and then I take this leading order of the expansion of the YLMs. I'm not going here in any mathematical detail. I'm just telling you this. You can calculate this from the spherical harmonics, and this is the final result. I just want to say, why is this result more or less your classical picture? So this guy, you see, n is very big. So this function, let's look at the spatial place and then look at the angular part. But what is this thing? So this function r n minus 1 e minus r n a 0, when n is big, n is 3 billion or something, this function as a function of r will look something like very peaked. And what we are going to do is we're going to calculate, and this peak will correspond to the distance with this particular angular momentum from the origin. Okay, so how do we get this peak? We take this function, we take its derivative, and we calculate this distance, which is the peak here. This is this R max. What is this R max? If we neglect these small fluctuations, which are quantum fluctuations around this R max, that is the position of the particle. There will be tiny fluctuations, but if R max is huge, but this is very small, then we can neglect these fluctuations. So it's kind of easy to take the derivative of R n minus 1 ER to find this maximum, and 0, that is equal to n minus 1 R n minus 2 E minus R over n A0, this n is important of course, minus n A0 R n minus 1 e to the minus R n A0, all this is equal to 0, because I'm looking for the maximum. So immediately I can, of course, get rid of this exponential. I can get rid of this and this, but here I have minus 2, so here I'll have 1 over R max. So okay, yeah, so now I have 1 over R max, and here I have n, 1 over n. N minus 1 is n, because n is very large. So I get R max is equal A0. That's obvious. It has to be have these units. But you see, here I have 1 over n, and here I have n. So when I multiply, this becomes n squared. Now, okay, maybe you are young, so you don't care at all about the history of quantum mechanics. But this radius is the radius of Bohr that he calculated with the old quantum theory, based on the assumption of the fact that the particle has classical trajectories, but which are discrete based on the angular momentum. So this is exactly what Bohr predicted with the old theory, which is not relevant, but it's kind of neat that you can get it exactly as you wanted. So here the picture is, so let us complete the picture. Now let us look at this guy. When n is large, what happens to the sinus theta? What is sin theta to the power n minus 1 when n is much bigger than 1? Well, depends what is the value of the sine theta. If sine theta is less than 1, you have some function less than 1 to power something big. What is that in the limit? That is 0 for theta not equal pi over 2. But if theta is pi over 2, and of course you can quantify this a little bit better than this. What is sine theta? 1. 1 to the power something big is 1. And what does this mean? Essentially it means that the angle is fixed. Only when the angle is pi over 2, you have some contribution to this wave function. And what does that mean? It means that you are moving in a plane, like in Kepler's program, like in classical mechanics. Of course, the final thing is that I choose this phi in this way, and that means that the total angular momentum is the same like the azimuthal angular momentum. So here, motion in a plane. Plane, I spell like that. Motion in 2D. I mean flat surface in 2D. There's some mathematicians here. So, how do you write plane? With I, N, or N-E?
A-N-E.
And with I, N, okay. Motion in a plane. Okay, and the total angular momentum is similar to the azimuthal and L is n minus 1 is large. M is equal L. So this is a classical Bohr-like motion. It's not exactly classical, right? Why is it not classical? In classical mechanics, what is the radius? The radius is fixed by the initial condition. You give this planet around the Earth, you give it some momentum and it starts rotating. The initial condition determines that. In Bohr's theory, the radius can have this value and n can be some integer. So this is what I mean by classical Bohr-like motion. You have, which means the following, that you have either this trajectory, or this trajectory, or this trajectory, or this trajectory, or this trajectory, all of them in the plane, and you can find in one of them. That is Bohr's model. So in Bohr's model, the electron is not a density in space. It's not a probability density. The wave function is not a probability. It doesn't exist even the wave function. You have one trajectory. The trajectory is like a classical trajectory. The particle goes around here, but it can go here, it can go here, it can go here, but it cannot go in between. That is the start of the quantization of the quantum mechanics. The picture is wrong, but it gives you some insight. In the limit of high quantum numbers, it still somehow works, because Bohr was a clever guy, so he said something what was not totally correct, but was not totally wrong. That's why Bohr is one of the fathers of quantum mechanics. He was the super important figure here. But eventually Schrodinger, the young guy, came and took the fame away from the older guy, Bohr. Bohr was really important. One reason he was important because he was the only guy who could fight Einstein. Because Einstein was against all the quantum mechanics. But Bohr was the guy who could tell Einstein, you know what, okay, with all due respect, you are wrong. But the young guys could not say that, so he was very important. Anyways, that's a little bit of gossip on quantum mechanics. Okay, I would like now to briefly discuss the spin from first from a slightly physical point of view, and also I'd like to explain a little bit more on how you can perform experiments that will verify the foundations of quantum mechanics from the point of view of measurement. This, in the book of Kohen-Tanuji, I think in chapter number 3, he discusses two-level systems, and he discusses the so-called Stern-Gerlach experiment. I'm going to briefly discuss it, but if you really want to see how to check the foundations of quantum mechanics, you should read this chapter in Kohen-Tanuji in greater depth. So, first of all, from the point of view of spin, I mean, how would you measure a spin? How would you prove experimentally that such an object exists? So, before answering that, you can ask an even simpler question. Let's say you have a system with orbital angular momentum. How will you know what is the quantum numbers of this system, that it is rotating, etc.? What will be the experiment that will give you this? Of course, we found this already in the hydrogen atom, but this is just theory. How do you measure in experiments? So do you have some idea, one method? Or so let's say you have a charged particle, and let's say it's classical for the beginning, and of course I'm thinking about, let's say, the electron in the hydrogen atom or some atomic system, and you have this classical motion of rotation. This classical motion of rotation of the electron, it generates, what does it generate? It generates a current. That's what you said? Yeah. So it generates a current. And what is a motion, let's say you have a motion like this of an electron around the center. What does it create? It creates a magnetic field, that's true, but it is a moment, a magnetic moment. That is, you have it's like a small, this I guess you studied in classical mechanics. You have, these small rings in which you have a small current flowing, and you can think, of course, the electron is not in a ring. There's no real ring, but you can imagine that the orbital angular momentum will create some current which is rotating like this current in the ring. It has a finite size, let's say in the hydrogen atom, like the ring has a finite size, right? So this will create a magnetic moment. And now what will happen? How can you measure this magnetic moment, or what is the energy of the system? You can measure it in the following way. You apply a magnetic field. If you apply the magnetic field to a magnetic moment, you know that the classical, so this is a magnetic moment. I mean, this is the physical realization of the magnetic moment. The magnetic moment we will denote by M. And the classical Hamiltonian, CL is classical, is minus M dot B. So B is going to be the magnetic field. And simply said, if you have, let's say, the rotation is like this, then the direction of M is upstairs with the right-hand symbol, right? And then the B is in the same direction. That means that if, for example, here you have like this, and let's say the magnetic field is out of this will be the minimum of the energy, right? When the direction of the magnetic moment is the same as the direction of the external field, this is the minimum. So this energy, on what does it depend? It depends on the angle between the direction of the magnetic moment, this is this dot, and the magnetic field. This, you all know this, or should know this from classical mechanics. So essentially this is the Hamiltonian of a magnetic moment in a magnetic field. Very simple thing. And the minimum of energy is when these two guys are aligned in the same direction. If they are oppositely aligned, then you are at the maximum of energy. And if you are at some angle, it just creates you some moment that will, that's why you have not the highest energy. The lowest energy is the stable state. So if I have something like this, and this is the direction of the magnetic moment, and then I, take it a little bit out, the magnetic moments want to push it back to the stable state. So this is the minimum of the energy. This is the state where it will prefer. I'm talking about the minimum of energy because, of course, That would be kind of the ground state of the quantum system. But let us, okay, think about this a little bit. How will we model the quantum analog? I mean, how will we quantize this thing? So the general idea, or the simple idea, is this M, what is it proportional to? It's proportional to the current here, right? If you have it is also proportional to the size, but the more current you have, the bigger is your magnetic moment. And what is this proportional to? In quantum language, it's something that you have learned. So in quantum mechanics, we take M proportional to L, which just means that if this is proportionality which is intuitive. I'm not going here in full details because we don't have time, but it just means, let's say the particle is faster. Oh, magnetic moment is bigger. The distance, like the size of the ring, is bigger. Also this L is bigger. So this M proportional to L makes some sense in quantum mechanics. To be more specific, and again, I'm not going into the details here. Maybe you should, I hope you'll learn it a bit in more depth with Richard next semester, or in quantum mechanics too. We define the magnetic moment, and B is for Bohr. It's defined like this: Q h bar, this is the charge of the electron, 2me. This is only for the electron. For the proton, you'll have a different mass. So this is the magnetic moment of the electron. This particular value is minus 9.27 10 to the minus 24 joule per Tesla. Doesn't really matter. The point is the following, that M is equal to this magnetic moment over h bar times L. So actually this h is redundant, we define it here. Now you see this mass here, why does this make sense? In L you have the momentum. When I divide it by M, what do I get? The velocity. And what you care about in the current is the velocity, not the momentum. That is what is important to create bigger current, which creates bigger magnetic moment. Of course, Q has to be finite. If there's no charge, then there will be no magnetic moment. So this, I'm not claiming I'm proving this here. I'm just saying what is the general philosophy. So this means that I can now do the following. I can make an experiment in principle. So the idea is, okay, let us do an experiment, and this experiment is called the Zeeman Experiment. I can take this thing, I can take the Hamiltonian, which is now already an operator. This is the quantum Hamiltonian of the magnetic moment, and it is given by, let's say B is B0 in the direction of Z. So, and here B is fixed, some magnetic field in some direction, and this direction I call Z. And then I just plug in these things, I get minus mu B over H B0L. Sorry, LZ. Because there is a dot here. This is LZ. So what does this Hamiltonian mean in the experiment? Let's say you have a system where you have L equals 0. What does it mean when you apply the magnetic field? What will happen? Nothing, because M is equal 0. But let us say L is equal 1.
Why is this the Hamiltonian?
Why is this the Hamiltonian? I told you. This is the classical Hamiltonian. Then this is okay?
So, okay, I didn't understand the CL.
The what?
CL
is classical.
The CL is the classical Hamiltonian. I always write down first the classical Hamiltonian because I know the classical Hamiltonian from other courses and I understand it. After I understand it, I need to quantize something. I don't quantize the magnetic field. I quantize this M. And I claim that this M is proportional to L in order to get this current. And if you think a little bit about the proportionality coefficients, you get these numbers. Okay? Then I chose B in the Z direction. So M dot B, if this is LZ times BZ. If I would choose X, I would get LX, but this is all the same. So this is the Hamiltonian. And when I apply, of course, when B equals 0, then nothing will happen. But if B is finite, then I'll get a splitting. In this case, into 3 states. M equals 0, M equal 1, actually minus 1, M equal 1, because of this minus sign. But this minus sign is actually cancelled, so it's like that, because here you have also a minus. So what is this? Just to summarize, you have some system. Let's say the electron in the L equal 1 state. You apply a magnetic field, and now you neglect the interaction with the charge. You cause a splitting of these energy levels, or this state, into 3. Okay? And this is how you can measure the degeneracy of some level, by applying a small magnetic field, and you get this splitting. What will happen if L equals 2? Then you'll get 5 states, because the degeneracy was 2L plus 1, and you have 5 states. Now, this indeed is found in many experiments, but there are other experiments, and there are other experiments on some systems. What do they show? For some systems, you have a state, and it's split into 2. Maybe even this type of state, L equals 0. And why is that? Because the electron has a spin, and the degeneracy of the spin is 2. Spin up and spin down. So a few weeks back I taught you the general angular momentum. We worked with operators, with the commutation relation, and we derived the spectrum. We showed that there exists spin half and spin integer. No, integer and half integer. They exist for some mathematics. This simple, relatively speaking, Zeeman experiment can take a system, and by applying a constant magnetic field, and then you need to detect of course you need to detect the splitting. So the splitting is detected, let's say, by other methods, by optical methods. You can find these 2 states depending on if the system has a spin or not. You can get some more complicated stuff. I mean, there's also spin 3/2, then you have 4 states. It's a jungle. I mean, atomic physics is a jungle. You have many atoms and many different phenomena, depending on which level you look at. Actually, consider the hydrogen atom. So you have 1s, then you have 2s, then you have 2p. Each one of these levels is split in different ways. So what I showed you, one level, then degenerate level, another general, each one of them can be split by this magnetic field into small sublets, depending what are the values of p and the values of the spin in that electron. So it's not something simple, but it's easy to measure. So I can measure this in principle for different states, for L equals 0, for L equals 1, etc., etc. So I have a lot of data, so I can really check this very, very precisely. It's not like one measurement. It's like for each L there is a measurement. And I can, of course, you see by this formula here, I can change B0. So when B0 is 0, this splitting is 0, right? Then I make the magnetic field a bit bigger. It will change. So I can measure the energy difference here as a function of B0. And if I do that, so let's call this delta E. So I have delta E as a function of B0. And you see it will grow linearly, right? Because LG gives you H times M. It will grow linearly with B. And the prefactor, what is the prefactor? It's mu B. So you can measure this mu B if you want and determine it to very accurate precision. This is what it is. Okay, good. So this is how you can convince yourself in a laboratory that the spin actually exists. And I didn't go here into the whole details, but only to some, just that you have some general clue. Now I want to teach you briefly another experiment. So this Zeeman experiment is important, but there is another experiment which teaches you on the foundations of quantum mechanics. You see, the problem with this experiment is, well, it's not a problem, but this is the experiment. It measures energy levels. It measures these splittings. This doesn't tell you anything about, let's evolve the system from some time to some time, then measure, it will collapse, then measure, it will evolve. All these questions don't even come into consideration in these type of spectroscopy experiments that just measure the energy levels. So we need other types of experiments to test the foundations of quantum mechanics. And the foundation of quantum mechanics, of course, is the Schrodinger equation. So the Schrodinger equation, especially the time-independent one, is really, there's no doubt that it works fantastically well, because you can take an atomic system, you can calculate the energy levels, you can go to the laboratory. I'm talking about things a bit more complicated than the hydrogen atom. And, this theory works, because after the hydrogen atom, people try to solve either numerically or approximately, let's say, the helium, etc. Every atom, people measure the energy levels compared to the predictions of the time-independent Schrodinger equation. It was tested much more than Newton's equation. So it works, for sure. I mean, the energy spectrum, fantastic achievement. But when we discuss things like measurement and collapse and things like that, well, maybe you can even say that is not part of the theory, because you don't measure things, you don't collapse things, all this. So how do you do that in an experiment? That's a totally different set of experiments, and one of them, and a famous one, is Stern-Gerlach experiment. And the story is something like this. We take a furnace. So this is a fire. It means that the atoms inside, these will be silver atoms in a gas, for a reason that I'll explain later. So here I have silver, Ag. I'm moving here like crazy because it's very hot inside. And you let some of them get out with velocity v. They go out in all directions, and many of them come out, but then you put another thing and they go through. Now, these atoms, silver, I treat them now the center of mass motion. I treat this classically. These are, like, for me, small spheres. What is the quantum part? It's the spin inside that I'll explain. So you have to differentiate between this atom has many electrons. It has many protons in the center. So it's pretty damn heavy. It's like you and me. It's not a quantum object. The wave function of the center of mass motion, it's classical. This is how I'm going to treat it here. But the spin inside of the electron, there's one electron there that has a spin. That is the quantum object. So you have to understand, an atom is a complicated object. It has many electrons, it has many charges in the center, and it has many degrees of freedom. But we are taking the center of mass, so you can think about it as simply a small sphere moving here in space. What is the experiment? The experiment is the following. I'll let it go. Here there's no magnetic field, and here I apply a magnetic field in the z direction. It's not a regular magnetic field like in the Zeeman effect. And here I put another detector, and I just want to record the position of these atoms coming here. And our classical prediction is that you have here a blurb. By the way, this is conducted at high temperatures, so it's a quantum effect that you can see in high temperatures. It's not that you always need to cool to low temperatures. I actually want to heat them so they'll be fast because I'm measuring just the spin. So, fine. So now I claim, and then Shun explain you why, that in a classical picture, these atoms that will go through here will be smeared here like a Gaussian shape. I don't care if it be a Gaussian or some smearing, but there will be some distribution. They cannot go, or some force is acting on the particles here. And this force, depending on the magnetic moment, can either pull them up or pull them down. I'll soon explain what exactly I mean. But the magnetic moments are oriented in all directions. So the classical picture here I have some small ring that you have some charge moving inside. Here I have another one, etc., etc., etc. But they are, you know, one guy has an angle like that, one guy has an angle like that, because this is very hot. So all angles are equally probable. So some guys are interacting in different, these are interacting in different ways. What is the interaction, or what is the force? Well, we just said that this is the classical Hamiltonian. You add m times b. This is the magnetic moment of these atoms. Assume for the time being that these atoms do have some magnetic moment. What is the real magnetic moment is some spin that inside. I'll soon discuss the specific atom. Why is it silver? So first of all, why do I use silver and not electrons? It's a bit strange, or is it not strange? I'm experimentalist now.
How you can have electrons?
What? How? Well, no problem. I can have electrons. I can heat this to very high temperatures. I'll have electrons. They're called plasma. I can get electrons. But I use here, what do I want to measure here? I want to measure the spin. If I have electrons, what will happen? They will have a charge. And if they have a charge, then you will have the Lorentz force. We don't want the Lorentz force. We want only the magnetic moment and B. And that means our system, this atom, cannot be a charged atom. It has to be neutral. That's super important. And that's why I measure the spin not on a single electron in this experiment. I measure it on a neutral system to delete the Lorentz forces that will also cause destruction and hell. I want only spin. So now what is this m? This m here, it will be proportional to in quantum mechanics. What will it be proportional to? This will be proportional to, I said that already, to L. And if it's a spin, it will be proportional to Sz. So in quantum mechanics, yes, we said already that m is proportional to L. But if you have a spin, that is orbital angular momentum. But if, let's say, you have no orbital angular momentum, you have only spin. M is proportional to S in the absence of L. So L is equal 0 for some reason. Here comes the cleverness of the experimentalist. He has to choose a system that is A, not charged, B has orbital angular momentum L equals 0, and spin, and only one from one electron, half. This, I'll soon explain, is why they chose silver. But you have to understand, these people are clever. They know what to choose. That's a good experimentalist. And this is indeed a very beautiful experiment. So it's super critical that they choose this silver. I'll soon explain a little bit more. Now, what is this exactly, this force? What did Stern and Gerlach do? They said, what is a force that will cause the particle to either go up or go down or stay in place? The force is when this B is also a function of Z. So they created a magnetic field, no, not of Z. This is Z, or how do I call this? This I call Y. No, but it's a function of Z. This was correct. You create a magnetic field that is changing with Z in this direction. Why is this important? Well, why is it important that it will change with Z? If it changes with Z, what happens? I have an F which is the derivative with respect to Z. So this is like a potential energy, MBZ. So I have a force. And why is the force important? You see, if there is a force acting on the magnetic moment is not changing classically. You have a force in this direction. Then to which direction will the force be applied? It can be either go up or go down. On what will that depend? It will depend on the moment. If you have this ring, these are rings. Some of them are in this direction, some in that direction, etc., etc. So some guys will experience a force upwards, some guys will experience a force downwards. Some guys will not experience a force because they will be in the wrong direction at all. And this, I claim, I'm not proving anything, will create a smear here. In a classical world, all the atoms will be, acting here. What is this length scale? It depends how long you stay inside here. What is the strength of the force? The longer you stay here and the bigger the force, the bigger you go up here. So this also depends on the geometry of the experiment. But this is not interesting for us. What is interesting is, I hope I convinced you that I get a blurb here. Now they did the experiment. If they got a blurb, this is not something squishy and mushy, nothing would be interesting. Then no one would remember this experiment. But what did they get? Well, assuming that this silver atom has spin half, what did they get? This is a measurement, essentially, of the spin. What did they find? So in reality, you have this system. You get the, of course, in reality, classical mechanics doesn't work. You have this system, and you get two peaks. The two peaks correspond to spin up and spin down. This is a very bad drawing. Or maybe the experiment is very bad, but if this is the chair, if this is the axis, then more or less like this. And again, how far they moved outward is important, but this will depend on how long they interacted with the magnetic field. We don't care about this. We just care about the fact that you have a splitting, and on your screen you get two spots. This one will correspond to spin up, and this guy would correspond to spin down. The reason is that the magnetic moment is proportional to SZ, because B is in direction Z. So the magnetic moment in general is proportional to the angular momentum. But the angular momentum can be orbital angular momentum or can be spin angular momentum. And in this case, it's spin angular momentum, and that's why you have here SZ. And then SZ, you can be either up or you can be down. And you have here not one atom, of course. So in measurement theory, we many times we have a system, it has a wave function. and you collapse the wave function to some state, and then you evolve, blah, blah, blah. Here, of course, you don't have one particle. This you can do in the last 10 years or so. These are experiments from nearly 80 years ago. So we have an ensemble of particles. Of course, the experiment is such that they are not interacting particles. The density of the particle is very low. So you measure on one, it happens to go to up. You measure on the other one, it happens to go to down. You have many particles. And then you get these two peaks. Had we worked with one atom, that wasn't Stern and Gerlach, it was much later in related experiment. If you had one atom, it would be either here or there by measurement. But this is a different era. This is the beginning of quantum mechanics experimentally. So hopefully you understand why you have spin up or spin down. Now, let us assume that instead of taking this system that has only spin and no angular momentum, let us take a system which has L equal 1. We could do this experiment there. And then what would you see? Instead of 2 peaks, you would see 3 peaks. Right? Because L equal 1 corresponds to 3 azimuthal quantum numbers, plus, minus, and 0. So this is not, or you can have more complicated things. So this splitting into 2 happens specifically for this system. This is not so trivial. So, but the hand-waving argument is the following. So just to summarize, we see that behavior is not classical. And 2, we can test the two-state spin system. This together with the Zeeman is a strong evidence that spin actually exists. Why do we have this silver atom? I don't know if these experiments tried with many atoms and then they found this one, or they were just clever. But if you look at the silver atom, its Z is 46, so it's a massive particle. It's built of krypton. Krypton is a noble gas, right? So I start with krypton, which is closed. That's the closed shell of this system, and then I have 4d10. So it's a okay. So now let me write it down, and then then I have 5s1. Let me explain. You'll see this type of symbols when you go to atomic physics. It's not so important, but the idea behind this formula is the structure of the table of elements, and specifically for silver. So the idea is that you start with, this guy contains many electrons. You see here I wrote only 12 and 1 electron. 10 and 1 electron. These are the number of electrons in this state. Now you know what is 4D. 4D is that the following thing. You have this atom. Let us neglect the interaction between the electrons for a while. Then you can think about these electrons. They populate the levels of hydrogen-like atoms. So I'm treating, and because you have many electrons, and because of Pauli exclusion principle, so you have you have all these energy levels. So you start populating. Here I have 2, etc., etc. You have many electrons, and then I fill in the full krypton, and then I fill this level, and it's totally full. And the important part is that this final electron that is living far away in this atom, there's only one, S. This quantum number is 5. That's the energy level of this state. Not important. S is important. It means that its orbital angular momentum of this electron is 0. And this is why this works in this experiment. It's half an explanation. It's not a full explanation. because what I'm claiming is that all these shells where the electrons are closer to the nucleus of the system are not contributing, and only the important part is this one individual guy that happens to be in the last state. It has zero angular momentum, and there's only one of them, and this one has a spin because it's an electron. This is an electron, and this will be spin up and spin down, and this guy, the claim is going to be influenced by this splitting effect, while all these guys, the sum of the whole angular momentum is going to be zero from my point of view. Now, we didn't study how to sum angular momentum. So an important question in classical mechanics, let's say you have a summation of vectors. Let's say you have a sum of two forces, give you the third force, right? The sum of angular momentums gives you the total angular momentum. If you have a system, you have one particle that has one angular momentum. You have a second particle that has a second angular momentum. The total angular momentum is the sum of the whole angular momentum, like the momentum, etc. We didn't learn how to sum angular momentum in quantum mechanics. This you will learn in next semester. It's called addition of angular momentum. It's a whole issue. It's not trivial. So I'm not really explaining you why all these guys don't contribute and only this one electron, but I'm trying to give you some taste, why it makes some sense. I'm not trying to prove anything. You have to understand, this beast is complicated. It has many, many electrons inside. So it's not trivial, so it's really magic that they were able to find this beautifully simple effect. But anyways, now, you can ask the following thing. So let us define now the reference frame. Okay, now we have these two states. And these spins here are in state up. And these spins here are in state down. Because you measured them here. This is the measurement. So these guys are in up. These guys are in down, right? So now let us say I want to check the postulates of quantum mechanics and do another measurement. How will I do it? Any ideas? I projected here these guys to spin up. Now what will I do? How will I do another measurement, let's say?
Another magnet.
What?
Another magnet.
Another magnet, and you are a theoretician, I think. You need another magnet, and what else?
In another direction,
in a small hole. So you make a hole here. Okay, so, and you let the electrons go through, the atoms go through. And another magnet. So, we can do several experiments. These are all explained nicely in Cohen-Tanucci. So, let us just plot this again. So, you get here all these atoms coming out. You have first screen, you choose one of them, one direction. You have the magnetic field, which depends on space. And I want to put it, I call this ZY direction. This is Z, and this is Y. This is a plane. So these magnets are in the plane. Then, okay, these guys are going here, and some of them are going up, and some of them are going down, and I create a hole here, and I allow them to go through this hole. This is the measurement. I pre-selected those spins with spin up in this experiment. Not, again, it's not the best experiment because it was done 80 years ago, because it's not on one spin, it's on many, but still, this is a pre-selection of an ensemble. Now, as this guy said, I will, oops, can you see? I will build a second magnetic field here. Oh, it's annoying. Now, this defines a plane. And I'm going to put it now in the same plane exactly. So this is also This is my zy. It's rotated because, but this is minor. What I mean is in the same plane. Because I can rotate it, and soon I'll do that outside of the board. And now I have here, sorry for this drawing, I have here another screen. What will happen? What will happen? What will be the same? Yeah, you're right, but be more specific. It will be the same. What does it mean the same? Same like this, up and down?
No.
Okay, so you're right. It will be same like this. That's what you meant. So, indeed, as you predict, you will see here something and here nothing. Why is that? This is the postulates of quantum mechanics at work. You performed first measurement here. You selected those particles with spin up. In between, they don't change. They remain in spin up. The magnetic moment now is in spin up. Remember, the force that is causing it to go up a little bit is on the center of mass motion, not on the spin, because it's the derivative of the B times the direction of the spin. All of them are up, then fine, they are here, that's all. So you see that I collapsed the system, and it remained there because I didn't have an Hamiltonian that will change the internal state, and everything is fine. But now I can do another slightly different experiment, and that is, okay, so this guy, sometimes Tanucci calls this the analyzer. So I can rotate the analyzers. In such a way that it will form an angle. In principle, I can choose any angle that I want. But let us just discuss the simplest case where I take this guy and I rotate it by 90 degrees. So let us plot this again. So I have here all this junk. You have these electrons. Now this is ZY. You have this first screen. This goes up. I cannot rotate it in my picture, so the whole idea here, this is ZY. And here, I'm going to plot this. This is a symbol, and this is the only thing. This I'll call XY. So it's 90 degrees. I hope you understand, because my capability of drawing is 0. So, and here again, in this plane, I have this magnetic field. Again, a gradient of magnetic field. Again, these guys, experimentalists, know how to direct them exactly to the system. And now I put here a screen. And now I can ask, what will I see? And what is the answer? What will I see if quantum mechanics is correct? Splitting exactly into two. You'll see two things. Of course, I can add now, if you want, another one, and then measure again sigma z, if I want. So if I choose one of them and then I measure this guy, what will I get? Splitting. Again, splitting. Not the one that I found at the beginning. I measured up. I measured sigma x, and this is a measurement of the spin in the x direction, because the magnetic field here, this x is the most important thing in this drawing. This is z, and this is x. So here I'm measuring, this projection measurement is the measurement of the spin in the x direction. So what happened here? I prepared it in the z direction. If you did the homework and if you listen to my lesson, then when you prepare a particle in the z direction, in a spin up, towards some direction z, in the x direction, it's a superposition of the two states, and it's a superposition in the x direction, which is exactly with this 1 over square root of 2, half probability to be there, half probability to be there. Again, of course, I could change this angle only slightly by, let's say, 15 degrees, so then I would have this peak bigger, this peak smaller. So I'm sure the students of Stern and Gelab did all these experiments by changing the angle slowly, plotting all this, and then you can really find out how many particles are here, and then you can add another one. So if I make a hole here, I'm in sigma x, and then I measure this guy again, then because I chose all the spins in the x direction in spin up, now it's a superposition of the z direction. So I measure again, I'll get 2. So here all of them were up. Here all of them were up in the x direction, or in the x direction plus x direction. And then here I will not get back what I got here, 1 peak, I'll get 2 peaks. So you can change these, you can play with 1 analyzer or with 2 analyzers. This was the breaking point of these measurement theories of quantum mechanics long time ago. And as mentioned, this was done with many atoms. But today it's even more exciting, I would say, or last 10 years or so, because now people are really able to measure small quantum system where you have only 1 atom or 1 ion or 1 electron, and then you're not performing measurements on ensembles of many of these guys, but you're performing experiments on 1 at a time. So this very nice chapter in cointology is something that if you are interested in the foundation of quantum mechanics, you should read again after this lesson or after the exam. So for the exam you will have 3.5 hours. You have 3 questions out of 4. You have, you can bring, you should bring, before the exam, actually you should bring it by, let's say, next Sunday, a sheet of equations that you bring, sheet of equations, and sheet of formulas. You bring it to Yaakov. Hopefully you can reach some agreement that all of you have the same sheet of equations. There are sheets like that from previous years, but they are not in English. And Yaakov said he will help you create this type of sheet. This sheet is for you. From my point of view, you don't need to bring any sheet, because if there will be equations, questions in the exam, which will demand, let's say, the wave function of the hydrogen atom in some state, I'll give it to you in the exam. I expect you to know something, basic equations, so you need to know. But I don't mind if you prepare these formulas, you want to do that, fine. But you have to bring it to Yaakov in advance so we can print it, and we will join it to the exam. You cannot bring into the exam any sheet that is not that sheet that we agreed. Do you understand? It's clear, this method?
The sheet is general, or?
It's for all of you. There's one sheet.
One sheet for all of us? So
in English. Yes, that we will print. You give it to me in a PDF file. I will print it for you. But you give it to me. Whatever you want on this sheet is fine. I don't care. I'm not checking this sheet. I don't care what you have in there. You can do whatever you want. It can be 8 or 9 pages, not a book. Don't solve problems there, yeah? That's what I mean. It's a sheet of equations, not a sheet of solutions. As for the level of exam, I hope it will be okay. It's generally speaking similar to level of exams that you can find on the internet. There are many universities, for example, in Israel, but for example, in the United States. I'm not so familiar with universities in China. I assume it's all the same, but my point is simple. You go to the internet and you solve all the exams of all the best schools in the world. Then you will be prepared to the exam. That's the way. The reason is very simple. There is one level of quantum mechanics which is more or less standard. This is a standard course, Quantum Mechanics 1. The definition of the level of the course and the level of exam, I'm not saying there are no fluctuations between different schools, but more or less everyone is asking the same set of questions all over the place with some variations of some very nasty professors. Or maybe intentionally or non-intentionally, I don't know, but that's the way to prepare, is to solve problems from the internet, and I think you'll be fine, and I hope you'll be fine, and that's all. If you have no questions, I'll thank you, and that's it.
Is it similar to your exams from previous years?
I have no clue, I don't remember. No, I'm kidding. This type of question is something that I never understood, because each time I give a question, I'm sure this is the easiest question. It turns out to be the most difficult, and when it's difficult, it turns out to be the most easy. So I cannot really comment on this, because this is something. So one guy will think it's difficult, some guy it's easy.
I'm asking if.
I told you what is the level. The level is you go to the best schools in this world. You know what they are. You go solve all the quantum mechanics 1 exams, and then you are prepared. Okay? That's it. So this is the level. I hope in the past I was the same level. I'm pretty sure I was, because that was the level. So isn't that not clear? He's a lawyer. Okay. Any more questions? Okay, I wish you good luck, and hope you enjoy your vacation. Thank you very much.
Thank you very much.